Okay, so as I said, I give you a very quick math tutorial about what is going to be examinable. So, but as I said, this week is pretty straightforward and very simple. So more or less like we help you review. So we have learned all these are the fundamentals. So you can see, so all the mechanical properties, it is related with the temperature, it is related with the strain rate and also the strain rate and also strain hardening, right? So this is one we have learned. Then we use this knowledge learned in the rolling and the forging. So rolling, we have talked about all these rolling mill design parameters. There's some of this calculation there. And the forging, there's not much calculation in forging, so there are different type of forging. So we focus on that one, and also the grain orientation issue in forgings. Okay, so these are just some like definitions. Okay, so the fundamentals is plastic deformation. So this is the most important thing. And we have the bulk one and the sheet one. So we basically only talk about these two. And also these are the illustrations. So since all these are not required, so there's no need. So basically just these two, okay? And also this is just rolling and also the forging, okay? So, but just, I think this no need. Okay, so just the one you're familiar with, okay? And this no need, and no need, okay? So the desirable, we said all the desirable mechanical properties are high ductility and low yield strength. And also the we said mechanical property are affected. This is very important. It is affected by temperature, right? So in general, ductility increase, but yield strength will decrease. Okay. So we have talked about the strain rate and also the frictions. Okay. And this one, no need. Okay. This one, please know, because this is quite fundamental for material scientists. So this what we call is engineering strain and stress. Okay, so what does this curve means? Okay, the UTS, this yield strength. Okay, so this is engineering strain, but just bear in mind. So engineering strain is not the one we used to do. It used to use it in metals. Okay, so in metals, most likely we will use this true strain, which is true strain. Okay, so this one because this is so fundamental, so please remember it. Hooke's law, and the E is the elasticity, stiffness, ductility, elongation, reduction of areas. Okay, so this so far we only talk about which is engineering stress and strain. Okay, so yield strength and the UTS. Okay, so the cross-sectional area is become smaller as it elongates. So this is a true stress and a true strain. Okay, true stress and true strain. Okay. Note for more small value of strain, the yield and this. Okay, so these two are roughly equal. Okay, so we said for small value, so that's why for ceramics, right? So most of the time people just don't differentiate these two. Okay, so questions. Yeah, any examination, so the formula is always given. Okay, so if for ceramics, these two are just people just actually share the same concept. Okay, but for metal, you have to be very careful because they are not equal anymore. Okay, the will be very different. Okay, diverge rapidly as the strain increase. Okay, because the ceramic you don't really have much change. Am I correct? But the metal you can have a very large change. Okay, so then we also there's for the flow, right? The flow stress. Actually, there's a very important concept here, which is this N. Okay, so most metal at room temperature strength is going to actually increase when you increase the strain. So we call it strain hardening. Okay, so strain hardening exponent. Okay. And also we said, so when N is higher, obviously N is higher, so the greater strain handling capacity, the stronger it will become as it's strained, okay? So we said, so toughness actually is just the area below, okay? So this one is toughness, okay? So the ductility normally is about this waist, so at which point you're going to get that fracture, okay? Okay, and also the we also have another one which is the maximum load, which is here. Okay, so these are different, but toughness is the area below this curve. Okay, so then this is just simple calculations. So I think I assume we have also give you examples that this one's not needed. Okay, but we have give you the examples already. Okay, so then we also explain if from atomic side, what is string hardening. So from atomic side, we know that because there's a dislocation there, so dislocation is entangled interference with each other. So this one, it will impeded by barriers such as grain boundaries, impurities, and inclusions in materials. Okay, so the most important thing is once you have more and more dislocations, so you will have more and more entanglement, more and more interference. This one make your flow or movement of dislocation is even harder. Okay, so that's what we put here. The higher shear stress required to overcome entanglement and impediment results in increased strength and hardness. So this one we call string hardening. Okay, so this one is a very typical one in metals. Okay, so we said the principle is coming from dislocation movement and dislocation generations. Okay, so this is the string hardening. So, and also I give you this, just let you know. So this is an edge dislocation, right? And if I have a edge, if I have a two edge dislocations now, so you can imagine they actually cancel each other out, or there's an entanglement. So one more difficult to move. So you can imagine this one, you want to move this way, so it will be one more difficult. Okay, so because become entangled. So this is a string hardening. Okay, and also the average flow is very simple, right? So simply just use, you just divide it by 1 plus n. These are simply just equations. Okay, and also we have done this together. And also when you have this polycrystalline metal, if they start with some more or less like equal X grains, then more or less similar, different direction are all the same. This one is we call it equal X grains, but if we give them some like string in this direction, right? So you can see this grain is actually elongated. Okay, so grain become elongated. So in this case, we call it is a preferred orientation. Okay, metal has become anisotropic. Since it's anisotropic, so it means it's a textured. It's textured. Okay, metal has a textured one. Okay, so in general, plastic deformation at room temperature cause increase in strength and decrease in annealing. So once you have this, right, so if you want to get rid of this anisotropic, okay, for some application you may need this, but some other application may not. Okay, so if you want to get rid of this, go back to something like this. So what you can do is you can use annealing reverse by heating, you heat up, so the crystal is going to recrystallization, means go back to something like this. Okay, so what you can see here, the stress and this is temperature, right? So as we said, all the others like elastic modulus, tensile stress, yield strength, all is going to reduce except the elongation, which is ductility is actually increase. Let me see whether I have record. Okay, recorded. Okay. So only the elongation actually is increased, okay, because once you heat up, so it's easier, much easier for you to do any deformations. Okay, so these are annealing. So annealing have 3 stages: recovery and recrystallization and grain growth. So you can see the morphology of the grains has changed one by one. So for example, in this recovery, okay, so you can see the all these things, the grain is roughly still the same. That's why the strength and hardness is roughly the same. Okay, so restored ductility without changing the grain structures. So at this stage, the grain structure doesn't really change. Okay, but the dislocation start to rearrange, okay, into a network. So it start to reduce this residual stress. Okay, so there's a diffusion and eliminate some of the crystal defects, but in general, so they just remove some of the small defects, but the grain size hasn't even changed. So that's why the strength doesn't really change. Then we come to the recrystallization. So you can see in this region, right, they start to have a new crystals. Before something like this, right? But now you have new crystals at the boundaries of deformed crystals. Okay, so new crystals, normally the new one, you don't have any string hardening, right? Because it's a new one, it's a fresh one. So that's why you can see it start to decrease the strength and also increase the ductilities. And the grain growth, which is the last one already. So now you have become bigger. So the grain become bigger. So in this end, in the end, hardness and the strength become much reduced and ductility increased. Okay, so these are the 3 stages. Okay, then based on different temperatures, we can divide it into cold work or hot work. Okay, so higher temperature means the formation operation can accomplish with lower forces and power. Therefore, 3 types of operations. Okay, cold work and hot work. Okay, so in the cold work, since we said cold work, right? So basically, you don't really increase temperature. So whatever shape you have, you have already had. That's what we put is a net shape operation, because you don't have any shrinkage, right? If you heat up high temperature, you cool down, you have shrinkage. So it will be much more difficult for you to control the occurrences and tolerance, and also the surface is very good in this cold working. Okay, the string handling, because in this case we have a lot of string handling, so the strings is going to increase. And also we said if something like start with this grains, but if you hand, so you make it grains, there's some shape there now. So grain may flow cause desirable directional properties. So maybe this direction, the properties is what you wanted. Okay, so all this depend on applications. So, but the thing is, if it's a cold work, right, so obviously you need higher force, right, and power because the material is not soft enough. So annealing required for further cold working. Okay, and also we said cold work. So the thing is because of cold work, right? Because of the string handling. So you can imagine the yield strength is keep increasing, right? Before roughly here. Now after one more time is here. Okay, so that's cold work. Okay, so and also we said cold work. So basically the yield strength increase, UTS increase, but ductility decrease. Okay, so that's we are very familiar with this already. Okay, and this is CW. So we have already explained one of the tutorial questions. So simply just read the graph and find value. And advantage, we have already seen better accuracy, close tolerance, better surface, string handling, and flow. Okay. And the disadvantage, obviously, you need higher force and ductility. And so, because once you have too much the string handling, so if you want further to do any like shaping, so it's more difficult. So you have to anneal it. Otherwise, you cannot do any further deformation because the material becomes too hardened. So it'll be more difficult to do further deformations. Okay. So this is cold. And then warm is something quite the weird in between. So so just above the room temperature, but below this 0.5 temperatures. Okay, so obviously because you increase temperature, so the force will be lower, power will be lower. Okay, and there's no need for the annealing. Okay, so we actually more focus on this hot work because it's above the recrystallization temperature already, so capable of substantial plastic deformation. So there's a strength coefficients substantially lower, ductility significant increase, right? Because we said we have already seen the graphs. We said if temperature is too high, strength is lower, ductility is higher. Okay, we keep saying this one. Okay, so string handling in this case is nearly zero. Why? Why this one? There's no string handling anymore because if you heat up at high temperature, so all this dislocation is actually being get rid of. So you don't have any dislocation anymore. So you don't really have much string handling. Okay, and also since the grain size become more like equal-axis, so you become to achieve more isotropic instead of anisotropic mechanical properties. Okay. There's no string handling because there's no string handling. Okay, but there's some the work shape of obviously like ductility is increased, so you're going to have all kinds of shape, lower power, lower force. If in the cold work, this material is very easy fracture, so you cannot use cold work. You can only use hot work. Okay, so in this case, the strength is anisotropic and not much work handling. Okay, so so sometime, okay, after this one, people still want to increase the temperature or increase the strength. You can still do a little bit cold work forming later. Okay, because the good thing for hot work is you can get all sorts of shape. Okay, compared with cold work. Disadvantage because you need cool down, so will be your shrink, so it'll be more difficult for you control the dimension, and the higher energy because you need heat up, right? And the poor surface finish because you might have a lot of oxidation. Oxidation is scales, and the tool life because you heat up, the tool life might get shortened. Okay, So, and also there's an important thing in this strain rate, okay, strain rate, which means how fast you change this deformation rate, okay. So it's a random velocity on the rate of deformation, how fast the material is deformed, okay. So the true strain rate and the instantaneous height of the workpiece being deformed. So as what we said before, so if you deform in a very fast way, so you're actually going to increase these strains, okay. So in most practical operations, so the strain rate is actually very complicated, because how can you determine the strain rate is depend on, because for this case it's simple, right? If just a cylinder or whatever, it's very simple. But if your work part is very complicated, so it's quite difficult for you to determine what is strain rate in different regions. Okay, can even in one part it can be 100 times difference, so make it quite difficult to control actually. Okay, and we'll also explain that flow stress is actually a function of temperatures. So at the hot working temperature, flow stress depends on the strain rate. Strain rate increase, so resistance to deformation increase. Okay, so this one we call is a strain rate sensitivity. So we already give you one example in the tutorials, right? So the strain is constant, and this one is a strain rate. Okay, it's related with the exponent. Okay. So this one no need, okay. And this one, so you can see, so with different temperatures, you can see the strain rate will perform in the different ways, right? So increase the strain rate will increase the strains, right? You can see because it's always going up, okay? So the slope is considered as a strain rate exponent, and the room temperature, you can see, is roughly no change, okay? So this is a strain rate sensitivities. So these are the take-home point, okay. Plastic deformation is because informing is very much is related with plastic deformation. So casting is related with solidification. Okay, you solidified from the liquid to solid. Okay, but casting, the forming is more plastic deformation, and also machining is just take away. Right, take away is a subtractive. Okay, so please bear in mind the big difference between three processes we have learned. So the bulk deformation, we have this, and sheet deformation, we have this, okay. And we know that engineering, strain and stress, true strain and true stress, okay. So these are very different, especially metal. We always use these two, okay. For this two, we more use for ceramics, okay. And strain handling, what is strain handling? We said is very much related with these dislocations, okay. And annealing, we have is a heat treatment. The purpose of the heat treatment is increase ductility. Okay, and lower the strains. Okay, so we have different stage, which is this, and cold work and hot work, and also increase the strain rate, increase the strains, strain rate hardening. So this is first part. So then we move to rolling. So rolling, right? Rolling is simply just two rolls oppositely. So then this one can squeeze forward. Okay, so that is a rolling. So the roll have two functions. One is provide the friction. The other one is squeeze the materials to reduce its cross section. Okay, so this one no need. Okay, but if you can just remember broom, snap, billet, because it's quite often used in industry. Okay, and also, all these things, if I'm testing your equations, any exam calculations, so I will give you all these equations, no worry, okay? But this one, not needed, okay? So this one, please remember, okay? Because anyway, if exam you, I'm going to give you the equations, okay? And force, also, what is L? L is this, L is this, okay? L is this one, which is the length of contact between the roller and the workpiece, okay? And all these are the equations, okay? So most of the time, this yield strength is giving up, okay? And flow stress, so this is another way you can use force divided by area, okay? So this is also another way, okay? And torque is also force. As we said, torque is, you just consider your force is acting in the middle of this arc, middle of the arc. That's why it is half of the L, right? But the force is in the middle. So this is assumptions, okay? And Okay, so this is power. So the power, right? So remember this equation, it is only applies to one row, and also this n is per second, okay? But in most realities, we have two, right? Two rows, and also we need change to this n from n to n prime. Okay, so once it's n prime, my n prime is RPM, it's a minutes. So because everything have to be in watts, so you have to divide it by 60. Okay, so this is the one for the real case. So this one is for the real applications. Okay, so then all this we have explained in quite details. Also one more in tutorials. So I assume all of you understand the things already. Okay, so this is the one. Okay. Okay, and also what happened, the microstructure change in rollings, you can see. So if the rock product have very large grain, so what happened? So you can see go inside, get elongated because it's still above this recrystallization temperature, right? So you will have this recrystallization. So in the end, okay, you can form this small and uniform grains, Okay, so this is rolling in hot rolling. Okay, so and also the important thing is because once you have small and uniform grain, so you will get an increased strength and hardness after you cool down. Okay, so and also please bear in mind we have two things you always need to do what we call a precondition. Precondition more or less like a pre-treatment. So a surface need conditioned, and this is for hot, but hot and cold is roughly the same. You have to remove the surface, make the surface very smooth, and also remove the scales, any oxidation you have to get rid of it. Okay, so rolling can be performed at room temperature. Okay, so the cold one have higher strengths and hardness because we have string hardening. Okay, so anisotropic, right? Anisotropic is coming from the preferred orientation. So this one no need. Defects, no need. Okay, so decompliant rolling is reduce the stiffness by compressive stress to opposing rolls, and forward slip, draft, and what are they? Forward slip not required, right? Draft, maximum draft reduction, mean flow stress, roll force, roll torque, and rolling power. And the hot surface, hot rolling, you need to have a surface treatment first, then carry out by this, okay? And cold rolling and the surface condition, so pickling of exit and carry out at room temperatures, okay? Better surface finish, okay? May have anisotropic properties. So this one no need, okay? And the last one, forging. Forging is just compressed, right? Either by compressive force or impact. Okay? So continue. Okay, so this one no need. Okay, so the hot one, so cold and the hot forging. Okay, so these are some like categories. So you just make yourself familiar with it. Okay, and also these are the three different types like open and close and precision. So what are they? So we spend quite a lot of time to explain about it in the tutorial also. So please refer more details either from the tutorials or from the lectures. Okay, so this is open. So in the open, right, we have this bearing effect if you have too much frictions, which means this region you cannot move, right? That's why. But this one, because we can move, so it will be more or less like a bearing effect. Okay, and also this no need. Okay, this one no need. This is just some names. Okay. Okay, so this is a closed die. So closed die. Okay, remember the difference is this flash here. The flash here. So what's the function of flash, which is here? These are the flash function, and also this one no need. Just some names. Okay, furring and edging. Okay, and this is precision forging. Means you don't have anything, no width at all. That's a perfect case. Okay, so this is a precision. Okay. And also we said if you compare with the machining, so you can see this is a green flow, in forge, right? So you can really change, the grain flow. Okay, so as we have already seen this one, right? So you start with this one, but this one is definitely a machine one, but this one is a forged one. Correct, right? Because we said the machine you just get rid of, so you won't change any of the greens, but so forging can change the green orientation, but machining cannot. Okay. So these are the comparisons between forging and machining. So we spent quite a lot of time explaining in the tutorial. So I guess all of you know it already. Okay, so take home point. Forging is compressed between two dies, either by compressive or impact. We have hot and cold, impact or press. We have open die forging and metal or flow laterally with minimum constraint. So if you have a lot of friction, you will have bearing effects, and this is going to be more pronounced in hot forging. Okay, impression die forging, closed die forging. Okay, so cavities or impression die imparted to workpiece. The thing is, you're going to form a flash. The frame is a stopper. Okay, so for precision, so there's no flash. Okay, so forging can change the grain orientation, but machining cannot. Okay, so that is all. So hopefully you get, I assume this is a simple 2 weeks. So hopefully you can grasp well without too much time to review this whole thing here. But bear in mind, Prof. Eugene's part, according to what he feedback to me is all his part is going to get exempt. So unfortunately, you have to spend some time to review his part. Okay, so thank you. So I stop recording.